As some of you may know, I've been giving more and more talks on this over since the last year. In fact, it's been exactly a year since I've come here, and it's the last one I gave starts off something following that. We live in a very unusual time. If you think about what we've gotten used to, we can, for example, plug a small wire into a hole in the wall, and out pop about 8 to 10 horses and clean our carpet. Or we can, turn a little key and out pop depending who you are, between 100 and 300 horses to take you to the grocery store. And when we fly across the country, during takeoff, we're actually using more than 100,000 horses. And the issue here is that our lifestyle has been shaped intimately. In fact, the primary reason for our lifestyle is the fact that we use a lot of energy, that we have been able to find the energy and we've been able to use this. And so this would be the equivalent, if you will, of the modern day equivalent of Roman emperors' legions of slaves. We have legions of horses. Around the world now, the typical energy consumption in the world is about 1 billion horses, 24/7, 365 days a year. It's a lot of horses. And there's always a cost to having so many horses. It's, how do you clean up the horse manure? And so part of what I'll be talking about is the equivalent of what's the horse manure and what can we do about it. So with that, I'm going to be talking about the possibility and what most atmospheric scientists, most scientists feel is the likelihood of global warming and its consequences, and potential solutions, and in particular the potential solutions that this lab can contribute to. Okay, so here's a summary of the temperature of direct measurements of temperatures since 1860 to the year 2000, and these bars here are actually the actual world average temperatures. And one of the scary things is that 19 of the 20 warmest years since 1860 have all occurred since 1980, and 1988 is probably the hottest temperature on record for the last 1,000 years, but if you look at other data. But this is a very short time scale. 140 years is nothing on geological scales, and so if you really want to talk about global warming, you have to go back further than 140 years to find out where we are. So if one does that, and you can go back, now data is going back 420,000 years, and even pushing now to 1 million years. This is data, the red curve is data over Antarctica. One measures this by looking at the ratio of oxygen 16 to oxygen 18 that's trapped in long-lived glaciers, which you can radioactively date. And so here we are at the present time, and that was the little bit of global warming you just saw. But the first thing that strikes you is, if this is global warming, well, then what's all this stuff? Well, this stuff is major ice ages. So why are we worried about global warming? Shouldn't we worry about a major ice age? And that's a legitimate question. The next thing to notice is that also plotted is the atmospheric carbon dioxide and atmospheric methane that's trapped in these glaciers in Antarctica. And you notice that they actually track unbelievably well. It's within the noise of this data. And then you say, well, you can't blame carbon dioxide and methane on people, because after all, Neanderthal man was about this time, and they weren't really significant in terms of putting in CO2 into the atmosphere. Okay, then the third thing you should note is that there seem to be very, very sharp rises, and it goes sawtooth down, and another sharp rise, and goes sawtoothing down. Okay, so now we're beginning to understand, there's a fear maybe in the question and answer period talk about these sharp rises, but these sharp rises could be very fast. They could be not a matter of thousands of years or hundreds of years, but even a matter of decades, you get a very sharp spike up. Okay, what's new in the data? Let me go back. Okay, why are we concerned about global warming if most of the time we've been cold? And during this period of time, North America, in fact, half the United States was covered in a permanent glacier. So what's new is the following. We're off scale now in the amount of CO2 in the atmosphere compared to the last 420,000 years. And because of that, we're in new territory. And so the question is, since we're in new territory, we can't look at a historical record. We need to predict climate change that might be due to increased greenhouse gases. Now, so this reminds me of a quote by the great American philosopher of the 20th century, Yogi Berra. And he said many things, but this is especially pertinent about these predictions. And so, since it's hard to predict the future, what you want to warm up with is how good can you predict the past? And I mean that tongue-in-cheek, but it is really something to be said about that. So here's the amount of carbon dioxide, methane, nitrous oxide since in the last 1,000 years. And you notice there's a sharp upturn around here. What's that due to? Well, that's the beginning of the Industrial Revolution. And so these are direct measurements. Now we can take these direct measurements, we can fold them into atmospheric models, and see if we can predict what's going to happen. So we're predicting the past, because we know what happened in the temperature. So if you do that, you stick it into our best climate models, and what you find is the red is the actual data of that increase of temperature by about 1 degree Fahrenheit. Or actually it's about 1 degree C, excuse me. And the gray is the you have your climate model, you have some parameters, you tweak them around, you have measurements of solar variations, volcanoes that throw up soot, that change the absorption of sunlight, and also its re-emission of infrared light, all that stuff, and you find that you can't really fit the data. But if you now fold in what we know we put into the atmosphere after the Industrial Revolution, you can do a reasonably good tweak of the model. Now, this doesn't prove that we understand it. What this means is that you can tweak the parameters to explain the last 150 years of warming. And as the models get better and better, then our confidence in predicting the past hopefully will improve. And if it improves enough, then we can confidently predict the future. So, with the caveat that these are tweaks of parameters to fit the data, and it's not really clear how robust they really are. Let's talk about the predictions. So suppose something miraculous happens, and then we're able to curb CO2 emissions in the next few decades, and then actually make it plunge by a factor of 20. What would the temperature of the Earth do? Well, CO2 stabilizes. Once CO2 is made, it's pretty stable. It cycles between the atmosphere, the oceans, the Earth, but it's up there for a long time, at least a few hundred years. This is showing over 1,000 years, but at least a few hundred years it's going to be up there. And the temperature stabilizes over a few hundred years as well. So it just continues to rise. So the bad news is, even if you can really get hold of something, you get super Kyoto Protocol going down here, that's what temperature does. And the sea level rises due to ice melting on land, and the sea level also rises due to thermal expansion of the ocean. Actually, the thermal expansion of the ocean is a bigger effect. Water warmer takes up more volume. So those are some predictions. And climate, just an increase in temperature is not the only thing. You increase the temperature, you increase water evaporation. It's a closed system, so there's more rain, there's more snowfalls. And so one is expecting more damage from storms, floods, and wildfires. And you're expecting significant property loss from sea rise, level rises, and the productivity of farms, forests, fisheries. All these things will change. So let's go quickly. This is Grinnell Lake in Glacier National Park a couple of decades ago, and this is what it looks like today. And so we already have a proposed name. It's non-Glacier National Park. Also, the ice shelves in Antarctica, also in the north, are breaking up, and this is a photograph of a major ice shelf breakup in Antarctica. We're seeing a lot more bleached coral, so when the sea temperature rises, the living organisms that are the coral actually die, and you just leave a skeleton, and there's a lot more of that appearing. The Great Barrier Reef is getting lots of this now. This is the weather and flood catastrophes over in each succeeding decade, and these are the total economic losses and the insurance losses. And the second insurer is an insurance company that insures insurance companies. Because if you have a major disaster like a hurricane or a big earthquake or something like that, the insurance companies need insurance because you also get a lot of claims. And so Swiss Re, the second largest insurance company, is saying they're jacking up the premiums more than doubling because of global warming. They say it's connected with global warming. We don't really know, but all we know is we're paying a lot more in disaster. And so this is an economic consequence. It's very noisy, but there's an average increase in the amount of forest, so-called northern boreal forest, burned in North America. And we do have more spectacular fires like this in Southern California, but this is, again, anecdotal and very noisy. These are predicted mortality rates in some major cities. So 64 to 91 are the current mortality rates, and what happens is, especially with poor people who don't have access to air conditioning, when there are hot summer months, people die, and it's now beginning to be reported in newspapers. And just to remind you, in August of 2003, there were over 3,000 deaths reported over France that were attributed to the 2-week heat spell. This is the increase of sea level since 1800 to now, and this is the scale. This is 20 centimeters from here to here, so it's increasing. A 1 meter rise means that you should buy property around here because it's cheap now. It won't be, but the only trouble is you don't know whether it's going to stop at 1 meter. It might stop at 5 meters. This is what we're hoping. The Kyoto Protocol wanted us to cap CO2 emissions here, and at this level of 550 parts per million, pre-industrial revolution is 275 parts per million roughly. We're right now about 380 parts per million. The Kyoto Protocol was aiming at capping it so that we would be at 550 parts per million, and so these are various scenarios, IPCC, but let's go back to predictions about what will happen if you cap either at let's say 550 parts per million. That's twice the amount of CO2 as pre-industrial days. And so this is the temperature scale. So if you're twice the amount of CO2, if you look here in the Midwest, you're down in here, you're 5 to 8 degrees Fahrenheit increase over here. And if you go to 4 times, you're in deep doo-doo. So this is optimistically the best we can hope for. And we're actually behind schedule on this one, significantly already. Okay, so that means the Great Plains, the great agricultural belt of the U.S. is, well, it's here in California, and it's in the Great Plains. And you're going up 5 to 8 degrees. You're not only going up 5 to 8 degrees, but the amount of water in the soil over here will be down by 20 to 30% if you're doubling, and 50 to 60 when you're over here. So if you're going up by 20 degrees average temperature and you have 60% less water, this becomes very desert-like. Okay, there's more good news. So here's oil, here's gas, here's coal, and these are renewables. This is what the world demand of energy sources, 71, we're now here, 2005. And so you see what we're using most of. We're using mostly oil and gas is projected to actually exceed coal because it is cleaner burning. Okay, so let me tell you more about the production of oil. So in 1959, a guy named King Hubbard, who was working at that time for USGS, predicted that the domestic oil production, this is in 48 states, would peak in 1970, and he was simply laughed off the podium, and he was wrong. It peaked in 1972. So this is domestic production of oil in the United States, and even with discoveries in Alaska, they haven't changed really significantly this downward trend. We're on the downslope of oil production in the United States. We're simply running out of oil in the United States. So there's production curves for the rest of the world, and it depends on assumptions. You have to assume that there's going to be a total amount of oil in the world, and it's a guesstimate. But if you guess, I think the USGS guesstimate was a factor of 3 more oil, correct me if I'm wrong, if there's more experts, a factor of 3 more oil than is the noun identified reserves would be the guesstimate of the total amount of oil. And then you make projections about the use and also about reservoir to production things, and you find that depending on your assumptions, and this is can vary by factors of 2. I mean, there are some predictions that we are cruising into the peak of oil production in the world today, but not many people are predicting beyond, let's say, 40 years from today that you're going to be not over the peak. So once you start going over the peak and you go into this decline, where you now realize it's the world oil reserves, I think it's a safe bet to say that quote, panic will ensue in the sense that the price of oil will go up. So $60 a barrel will look pretty inexpensive. So it's ironic. The total world production of oil from, so we're talking about 125, roughly 150 years max. What took about 100,000 years, or 100 million years or more to generate in terms of oil disappears in 200. Okay? And then gas will follow, because we're now thinking about liquefying gas in other countries, bringing it over in the United States and burning it in lieu of oil. Well, we have this is our forecast for coal. Now, coal, we have much more than 30 or 40, 50 years of coal. We have maybe 400 or 500 years of coal left. Now, coal is bad because it emits a factor of 2.5 times more CO2 per unit of energy than, let's say, methane. And so this is the projections now for new coal plants, and so that's scary, because once you invest tens of billions of dollars in coal plants, new coal plants, the economic will to not use them, they will be used. Let me put it that way. So what one needs to do is to think very, very hard about what to do now, because if you don't do anything now and you go ahead with these projections, 20 or 30 years from now, you've just bought yourself into a huge problem. The political will not to use those coal plants would be enormous, not only in the United States, but also in China, especially, because China also has incredible coal reserves. Energy from tar sands and shale oil is just as bad. It's horrible stuff. And for example, now in the tar sands in Alberta, Canada, they're beginning to extract in large quantity now, because oil is $50 to $60 a barrel, and then production costs for extracting the oil in Alberta is now dipped below $20 a barrel. So there's $30 of profit. And so about 20% of that tar sands is accessible by strip mining, and so that's what they're doing. They're mining it with huge shovels. They have natural gas in Canada. They use the natural gas to heat up the tar sands, liquefy it, get it out, and then they put the waste into a holding pond. until they decide what to do with it. The holding ponds are now the size of medium-sized lakes, and they're getting bigger. So that's another issue that hasn't been resolved, is what to do with that. So one analogy that I've been using is that suppose you're on a Pacific island, there's no escape off the island. This island's all you've got, and on the top of the island there's this lava flow coming down, and it looks like it's engulfed the entire island, and everybody's going to be killed. And so with a little imagination, you can imagine that this lava is going to consume you, your children, your grandchildren, whatever. So the village elders come and they have a little meeting, and some of them say, well, this is all sounds very ominous, it's terrible, but we can only work on a 2-year or 4-year cycle. So we can't deal with this. And other village elders say, well, look, if we take some of our smartest people to think about how to divert the lava flow, this will have economic repercussions, and I don't think we can afford to do that. And others say, well, you know, it will have economic repercussions, but shouldn't we be sure whether it's 100 years from now or 300 years from now that this will happen before we start doing something about it? And the ones I like best are the free market islanders who say, not to worry, we're very clever people, and when the lava is just at the border of our village, we'll figure out something. Now, we've heard all of these arguments, but it's hard to imagine that this conversation would ever occur on this island. Why? Because it's so visible. Every morning, you get up, you see the orange glow. Every night, you go to bed, you see the orange glow. And it's less visible, global warming is less visible, and it's less visible that you're running out of oil and gas. So now, energy conservation is very important, and it can actually readjust the baseline by factors of 2 to 5. We consume more than a factor of 2 more than Europe in terms of energy per GDP, and that's very important because as you look for technological solutions, if you can divide by a factor of, let's say, 4 or 5, that could change a lot of things. Okay, so let's look at possible solutions. There's nuclear fusion, and we have been looking at this for 60 years. We will continue to look at it, and I think we should, but we have been looking at it for 60 years, and the people who are working on it actually say, even if ITER is a success, this is the large consortium that's going to be costing $5 to $10 billion, say at least $5 billion. That's not a commercial reactor. That's still a scientific experiment, and so you're a couple decades beyond that for commercial viability. Okay, and that's going to be completed around about 30 years from now, 25 years from now. So we have to find something shorter term than that. And there's nuclear fission, and there are 2 issues: waste and nuclear proliferation. There's really a third issue, and that's fear of nuclear power. If we go to 3 terawatts is the current power consumption of the United States, the power consumption rate, and that would mean a new gigawatt reactor every week for the next 50 years. So that generates a lot of waste. So the amount of nuclear waste we have right now can fill up Yucca Mountain. And so you need a couple more Yucca Mountains. And so that's a problem. Now there is some hope. There's some hope emerging that with recycling and actually introducing fast neutrons into even commercial reactors now, you can burn down the waste, and that varies from a factor of 10 to a factor of 100 reduction in nuclear waste. The downside is that when you recycle, the typical recycling is that you separate out plutonium. You have U2 there. You're actually making some fuel as well, so it's quasi-breeding. But you're burning down the stuff. You're reducing the waste by a whole lot. But you now have a technology where you separate out the plutonium, which could get into bad hands. So that's the U.S. policy up until now, is that we don't recycle. France, England, Russia, and soon Japan. Those 3 countries have been recycling for decades, and Japan will start. I heard rumor, I don't know technically anything about this, that it may be possible to recycle and burn down without separating out the plutonium, which would be great. Okay, so that's something we should look at. This is long-lived radioactive waste, and so this is years. Remember, this is 100,000 years. Remember, 500,000 years was the 4 ice ages. So that's another issue having to do with long-term waste storage. If you want to get down to this level, let's say we relax a little bit and get down to this level, you're still talking 200,000 years, and it's a long-term problem. Okay, so what's left? If there's not fusion, if there's not fission, and we don't want to use tar sands or shale oil or coal because of the global warming issue, the only thing left really is some form of solar energy. Now, you think of solar energy in terms of photovoltaic cells, but long-term, big-time uses has to rely on the fact that we got to get the production of cost of electricity down to somewhere around this level before it's going to become viable. And so we need a factor of 5 to 10 before large-scale use of this would kick in. There's another form of solar energy is wind. That's made much more dramatic strides. This is the cost of generating electricity from wind. It's plunging down. Just to put a normalization, this is the cost of generating electricity with gas. Now that's pretty good. You're within striking distance. The downside is that no, there's actually no downside relative to burning coal. There are some downsides, but not relative to burning coal. One of the issues about generating electricity from solar, like photovoltaics or wind, is that you can't store the electricity. So if this ever becomes a big deal, as in a 20, 30, 50, certainly a 50% deal, you have to, the grid can take care of a 10 or 20% thing, but it can't take care of 50%. So when you need a way of storing the electricity in terms of energy that you can produce on demand. So this is getting good, but it's limited. If the solar gets good, this stuff, photovoltaic gets good, we'll need to convert electricity. On demand, you can pump water up a hill, but there's not enough water in the United States to pump up hills to do that. There's another possibility, and that's photosynthesis, because nature's actually found a way to convert sunlight. See, it uses CO2 and converts it into stuff like this, and this stuff is a form of chemical energy. Photosynthesis is a pretty complex process of capturing light, transferring the light energy into what is called reaction centers, where first electron transfer, and finally you're making a chemical bond that could be easily broken. You actually, in most photosynthesis, let's say in plants, you're actually using the equivalent energy of 2 photons in order to establish a chemical bond. Once a molecular complex is sitting there holding the equivalent energy of several electron volts, 3 electron volts of energy, they tend to explode. It's a lot of energy concentrated in a very small set of molecules. Okay. And so that's the problem. Now, it's also a problem with nature, and nature has found a way. You can actually sense when this photoreaction centers are no longer working, so there's a little molecule goes in there, picks it up, tosses it away, plops in a whole new one, and off you go again. And so if we're going to make something that is a biomimic of photosynthesis, we need some self-repair mechanism. We don't know how to make organic materials that can hold 3 eV of energy for enough cycles to last. You would want it to last at least, let's say, a decade. Silicon lasts 3 decades out exposed to, in satellites. But organic stuff tends to disintegrate. And so that's a major challenge. And so the challenge really is the chemical conversion and how do you get self-repair in these parts. Now, let's go at a shorter-term possible solution. If you look at that plant that we have, the plant can convert sunlight, CO2, water, nutrients into biomass. mostly in the form of structural members. If you take most of what a plant is, it's the cell wall structural material of a plant. And so there are two possibilities. One could improve plants to make them self-fertilizing and drought-resistant and pest-resistant. So this is genetic modification of a plant, so it uses less water, so it grows even faster than your normal weed, and makes a lot of biomass very efficiently. Right now in the United States subsidizes U.S. farmers. I've heard 3.8 billion, but I've been corrected by someone else who said no, it's only slightly over $1 billion. But let's say it's between $1 and $3 billion that the government, U.S. Federal and state government, pays American farmers to grow corn, and you take the corn and you turn it into ethanol. Now, that sounds all very good and fine, except if you look at studies, including people at our lab and on campus, this is the amount of energy you have to invest. This is the net gain of growing corn to make ethanol, and on this side it's a loss, and on this side it's a gain. So depending on who you are, it looks like, generally speaking, it's a net loss. For every unit of energy of ethanol you get from growing corn, you have to invest about 2 units of energy, if you're, let's say, believe TAD, in order to grow the corn. In terms of CO2, well, you know, the corn is photosynthesis, so it's fixing CO2 out of the atmosphere, and it's converting it to fuel, and so when you burn the fuel, you release CO2, but it could be a net positive, but it's not. So this is the amount of CO2, if you prefer, in order to get a certain amount of energy, if you burn methane, this is the amount of CO2 you use to grow corn. So it's not there yet. So I think right now, with current technology of growing corn and turning it into ethanol, we have to get it, we want it to be on this side of the diagram, so we're burning less CO2. Now there is a proof of principle. In Brazil, sugarcane is grown, and it seems to be nearly breaking even. And right now, commercially, it's more than breaking even. You can buy ethanol made from sugar cane to run your car at half the cost of gasoline. And in Brazil, about 20% of the cars are now called flex cars. There's a little switch in your car. You can switch it to burn ethanol, or you can switch it to burn gasoline. And if the price of oil stays where it is, most people, the car fleet will actually convert over to these flex cars in the next couple of years. So it's a sort of a proof of principle, but it tells you how much you have to improve. There's 3 crops of sugarcane a year in Brazil. Brazil's got a lot of sun, a lot of water, can raise this stuff. We can't raise sugarcane the way Brazil can. Okay, so now this is a favorite of Jim Woolsey, who's the ex-director of the CIA. It turns out the ex-director of the CIA is a real energy conservation nut now. Now, it's not because he really hugs trees. It's because he thinks that this is so intimately tied to national security that we have to get off of oil. Switchgrass is one of his favorites. It grows like a weed. It's essentially a weed, and it's mostly cellulose. It's not growing oils or sugars. And so you have to convert the cellulose into ethanol or methanol. And so another thing that we can be working on this at the lab. We can also be working on this. How do you convert biomass into chemical energy in a more efficient way? This is the way we do it now. We build something like this that looks essentially like an oil refinery. In fact, it even acts like an oil refinery, and says it's a high temperature acid approach, of standard chemical engineering approach to doing this. Are there better ways? Well, we don't know, but again, nature has figured out ways of converting biomass into other forms of energy, these microorganisms, and we're actually in the JGI, we're sequencing this and other microorganisms. Why do you want to do that? Because you now know the set of genes. You can begin to identify those genes with chemical processes within the bacteria. And so you, again, learn from what nature has done. After you understand how these bugs convert cellulose into a chemical fuel, can we design either a better bug to do it, or can we, will that give us some clue as to an enzymatic way of breaking down the cellulose into chemical energy? And so that brings in the fact that we now have a new area called synthetic biology, and as many of you know, Jay is one of the real bragging points of this lab in terms of its application of synthetic biology. In this case, looking at what a plant that's grown in Southeast Asia can grow, artemisinin, and turn that into a drug that treats malaria much more effectively than the quinine-based drugs. The protozoa that causes malaria has now become resistant to the quinine-based drugs, and so this is a real problem. Malaria kills about 2 million people a year. And so if you develop a drug, in this case, Jay is working on trying to get an E. coli by inserting these genes into this E. coli. So it's not just one gene to make a single protein, but it's a set of genes to make this chemical. And he just, about a year ago or a year and a half ago, got a grant from the Gates Foundation for $42 million to make this commercially viable. Commercially viable is commercially viable to third world countries where malaria is predominant. So the target is $2 per course treatment. $2 is about a week's wages, but they're willing to come up with $2. They can't come up with $20. Okay, and so and then there will be a pilot company that will market it for a price that can be afforded by third world countries, and so that seems to be actually on target. In addition to saving people from malaria, Wynn hopes he can also help us use this same sort of synthetic approach to engineer bugs to produce ethanol or methanol or methane from cellulose. So you can now even think bolder. You can skip the biomass part and maybe think of making bugs that directly turn sunlight, CO2, water, nutrients into chemical energy. Private companies are beginning to do that. One of Craig Ventnor's new companies, a central part of it, it's a synthetic biology venture. The idea is they would put in a whole genome, an artificial genome, into a bug that would make it take sunlight, turn it into some sort of chemical energy. And so Ham Smith, who's the kind of, if you will, the brains and the magic hands behind Craig Ventnor's other successes, he's a friend of mine that I met about a dozen years ago, and he's in charge of this. He can now take little snippets of DNA, he tells me 45 bases long, single-stranded, put them all together and make a megabase piece of DNA. And so he's busily trying to mix and match and put in genes to try to do this. Okay, so I've outlined a few things. There's also electrochemistry approaches to converting electricity directly into chemical energy that we should be doing and will be doing. I personally think because of the rapidly advancing fields of synthetic biology, nanotechnology, molecular biology, married with the physical sciences, that these are some of the most rapidly advancing areas of science that we have. And so so this might be a good bet. At least it hasn't had 50-year history of not producing. Maybe because it's where the advances are the fastest, one can be optimistic. So if you think about our national concerns, but they're really international concerns, if you ask most Americans what they might be concerned about, certainly national security, which is intimately tied to energy security, and there are not so hidden costs of our present energy diet. It's also tied to economic prosperity, because in the future, if we aren't able to operate more efficiently aren't able to get alternative sustainable sources of energy, we will be in big problems because oil will run out and then followed shortly thereafter by gas. And so the cost of energy is a major factor in our economic prosperity, and of course there's global warming in the environment. And so energy is at the center of all these things. And so for this reason, it's arguable, in fact not only arguable, I think it's obvious, at least to me, that getting sustainable CO2 neutral energy is the most important technological or scientific challenge we face today in terms of trying to do the science in order to get a technology that will enable us to go forward. And if you put this, it's not basic science, that's true, but actually it will take some basic science in order to do this. And so there's examples of this, and I'm reminded in history of a place where I used to work for 9 years, Bell Laboratories. Bell Laboratories is noted for many, many things, inventing many things, notably the transistor and the laser, but they've invented actually a lot of what goes now into modern communications and modern electronics over the last 80 years. This is a picture of the first transistor. Now, when you think of the invention of the transistor, you think of the people who got the Nobel Prize for the invention of the transistor. But in actual fact, there was a lot more that was going on. For example, they had to develop material science in order to purify silicon and germanium at the high enough purity that they can actually make usable devices. And then they would have to be able to dope these semiconductor materials in very controlled ways. They had to understand the physics of the electronic structure of these semiconductor materials, the surface states of these materials, the details of what was really happening in the p-n junctions, and so on and so forth. So en route to inventing a transistor, they actually were laying the basis, and continued after the invention for the next 20 or so years. They laid the basis for much of modern semiconductor device electronics. Okay? It was just not a single solitary scientific, quote, invention slash discovery. It was, a lot of great science had to be done, and it had to be done across many disciplines. And so in the late 1930s, people at Bell Laboratories and AT&T decided that vacuum tubes weren't going to work, scaling to better and faster and more reliable switching systems, because they essentially were dependent on heating a filament to red hot temperatures, and that filament would actually melt and be destroyed, and because of that you also had huge heat dissipation problems. So they wanted a solid state switch. So they encouraged a lot of scientists to get interested in this, and they began to form teams, and there was very rapid communication, if you read the history about this, of these little teams talking to one another on a daily / weekly basis. Very much unlike a university setting where you kind of don't want to talk to anyone because they might scoop you. Because there was a lot of talking within the laboratory, and because of that, this thing was developed in a factor 2 or 3 faster time than could have been developed in an academic setting. This is a quote of a well-known physicist, Nico Bloomberg, who got a Nobel Prize for his contributions in laser spectroscopy. He was one of the pioneers. He was the guy who invented the 3-level maser and was one of the pioneers of both masers and lasers. And this is what he said. You know, he never tried to make the first laser. He said, but fundamentally, industrial resource organizations had the support organization. They could put teams together and focus on a common goal, and in American universities you just putter along. Well, the great industrial labs are gone, and we're it. We're the next best thing, and hopefully we can even be better, but this is it. So so here we are, and we're pretty, let me remind you, in case you don't know, we're a very distinguished laboratory. Of the 14 Nobel Prize winners in science at Berkeley, 10 of them were employees here. And there are currently 59 members in the National Academy of Sciences. Let me give you the denominator. There are 2,000 members in the National Academy of Sciences in the United States. So it's 3%. Okay? So we are distinguished by any measure, not only distinguished among national labs, but distinguished among the very best educational institutions as well. And our budget has grown from where it used to be the heart in the days of Lawrence, high energy physics and nuclear physics and chemistry, and now it's this part. They still do great things, and in fact, an 11th Nobel Prize winner is waiting for discoveries of dark energy, but it's a very multi-purpose laboratory. A quarter of the lab does biology or biophysics. And so it's a very different laboratory, and if you think about the things we excel in computational sciences, in physics and chemistry, in nanoscience, material science, and life sciences, I hope I convince you that some of the things that look very likely can contribute to the energy problem, we've got those pieces. Okay? So the idea here is, how do we get something mounted much in the same vein as the invention of the transistor to work on this problem? So what should we do? Well, I think we're going to have to produce better predictions of global warming. I would love to see this laboratory, our best scientists get interested, and this is happening more and more, to really do the pioneering research. And by research, I mean a lot of it is going to be very basic research, just like a lot of very basic research had to be done in order to form the basis for inventing a transistor. So we can do a lot of basic research in fields that range from synthetic biology into nanotechnology solutions to better photocells and maybe better electrochemistry solutions. The idea is that you will actually do some science that can be the basis for a technology that will really transform the landscape of what we can do about energy. And we should also work on our leaders and convince them to take some action, because those predictions are getting scarier and scarier. It's looking now in the most recent studies as though methane led the rapid temperature rises. There's a lot of methane off the coasts of our continents, and one conjecture is they go shooting up suddenly. It's a phase transition. The methane frozen into ice becomes soluble, goes shooting up. Methane's about a factor 20 worse greenhouse gas, and then it causes this very rapid temperature spike. So it's a phase transition, means a little bit increase in temperature might mean a very sudden increase, and that's what we now think might have been the cause of those sudden things. So I think we should do all those things, but in the meantime, the world is melting. So with that, I will stop and take questions.